Welcome, Wildcats. I've been told that my videos are a little bit boring here. So the reason that I've been told that they're boring is because they don't have proper introductions. So here you go. I hope you enjoyed your animated intro. This is, in fact, the 1.2 homework. It's exactly like the 1.1 homework, except this one comes with an animated introduction. It is also going to be covering the 1.2 homework instead of the 1.1 homework, because this is the video for the 1.2 homework, not the 1.1 homework. So let's go ahead and hop right into it. So we are looking at 1.2, characteristics of function graphs. You guys saw a lot of different graphs. One of the things that we didn't really mention, but is pretty self-explanatory, is different intervals on which a graph is increasing, decreasing, or staying the same. So question 1 here is talking about just that. The graph shows a function that models the value v in millions of dollars of a stock portfolio as a function of time in months over an 18-month period. So, to the nearest integer, on what values is the function increasing? Well, it looks like it's going up from here to about here. And since they want the nearest integer, that would be 2. So it looks like from 0 to 2, this is going up. You can see how it goes up here, and then it goes down from here all the way to about here, and then from 13 to 18 it turns around and goes up again. So we have increasing from 0 to 2 and from 13 to 18. So on what interval is the function decreasing? Well, that would be between the values that it's increasing. So it turns around and starts going down about here at 2, and it goes down from 2 until 13. So from 2 to 13. So that's actually a type of question you'll see a lot, whether or not a function is increasing or decreasing over a specific interval. So the graph shows a function that models the value v in millions of dollars of a stock portfolio as a function of time t in months over an 18-month period. Same question. Graph is a little bit different though. So always double check the graph, make sure that it's either the same or different. Identify any maximum values and minimum values. So it looks like the maximum's about right here, and that's just over 7, almost 8. So a maximum value of about 7.8 occurs at approximately 3. So maximum value of 7.8 occurs at approximately t equals 3, which would be a minimum value of about 1.8, which looks about right at about 14. So B. Correct. Number 3, graph shows the exact same header, different graph. So this graph, by the way, this is one that we didn't study, and you will not study it unless you take pre-calculus. This is called a sinusoidal graph. What are the functions domain and range round values to the nearest whole number? Well, domain is easy. We start at 0 and we're going to 18 months. So domain is 0 to 18. Range is, it looks like the lowest we have is 1, but it does look like it touches. And the highest appears to be, it looks like it's just over 7, but they want us to round to the nearest whole number, meaning 7. Next question. The table of values gives the probability for getting all 5s when rolling a number cube n times. This is actually a problem from probability and statistics that you will study more in depth if you go there. However, you don't need that much info to be able to solve this. So they want us to know, is this increasing or decreasing? Well, 1 over 6, 1 over 36, 1 over 216, 1 over... So the number on bottom is getting bigger while the number on top stays the same. So that means as a whole, it's getting smaller. So as the number of rolls increases, P of n decreases. This implies that the more times a number cube is rolled, the less likely it is that every roll is a 5, which honestly makes a lot of sense. If I have a bunch of dice and I roll them all, not a very good chance that all of them turn up 5. Next question. Number 5. Table of values gives the probability for getting all 6s when rolling a number cube n times. So same table, because it doesn't matter what number you're talking about. If you're talking about a single number, then you're gonna get the same table. What is the end behavior of P of n? Complete the explanation for the significance of this. As n increases without bound, P of n, so basically the more dice that we roll going over to the right, the closer and closer the probability gets to what? Well, it's never going to be exactly 0, because there's that 1 in a billion chance that they all happen to be 6s, but it gets close. So P of n approaches 0. The table shows some values of a function on which intervals is the function's average rate of change positive. So on which intervals is the function's average rate of change positive? So if I go from 1 to 2, 1 to 2, my rate of change is definitely negative, so not that one. From 1 to 3, I start higher than I finish, so the rate of change would have to average a negative number. For C, 0 to 3, I start at 55, I end at 70, so my average rate of change would have to be positive. D, from 0 to 2, I start at 55, I end at 45, so my rate of change would have to be negative. From 0 to 1, I start at 55, I end at 80, so my rate of change would have to be positive. And from 2 to 3, starting at 45, ending at a larger number, 70, so it would have to be positive there as well. Now you could actually sit down and do the math and figure all of these out, but to me it makes more sense to just look at the start and end point. If your end point is higher than your start point, then that means your average rate of change is positive. If your end point is lower, then it's negative. What is the function's average rate of change over each interval? Okay, average rate of change over the interval -3 to 2. So if we're going from -3 to -2, then what we need to know is at -3 we are at 0, and at -2 we are at 2. So we take the second number, in this case 2, subtract the first number, and then take the second number, -2, and subtract the first number, so minus -3. That's the same as +3, which is 1. So 2 divided by 1, which is just 2. That is not focused very well. And that pen is not writing very well either. I have another one though. No. Alright, new pen. So that's how we're going to do all of these intervals. So in this case, the rate of change is 2. From -2 to 1, so if we're starting at -2 and going to 1, then what we're looking for is at -2, we're at a 2, and at 1, we are at, oh, looks like it's about -4. So, -4 minus 2 is -6. 1 minus -2 is, it's plus 2, 3. -6 divided by 3 is 2. But negative divided by a positive is negative. Once again, the easy thing to see here is that we are going from a higher number to a lower number, so we know that this should be negative. From 0 to 1. So -3 to -4. This is a little bit easier because we're only moving one space. We can see that. So since we're moving down 1, that we know since we're moving down, it's going to be negative. Since we're moving down one space, it's going to be -1. Since we're moving over one space, we're dividing by 1. So -1 divided by 1 is just -1. Again, we're only moving one space, this time from 1 to 2. 1 we said was -4. 2 is 0. So we're starting here, ending here, we're going up 1, 2, 3, 4, and over 1. So that's up 4 over 1. So our rate of change is 4. Now you might remember from Algebra 1, you guys did this with straight lines. You called it slope. Rate of change is slope for linear equations. When it's a linear equation, we call it slope. When it's any other type of equation, we usually call it rate of change instead. So the average rate of change over the interval -1 to 0. So again, we're only moving 1, so -1 is 0. 0 appears to be -3, so we're going down 3 over 1. Average rate of change over the interval -1 to 2. So this time we're actually moving quite a ways. We'll probably need to write this one down. So we're going from -1 to 2. That means we're moving 3 over. And -1 is 0. 2 is also 0. So we're not moving up or down at all. So that means it's 0 divided by 3. Since we're not moving up or down at all, the average rate of change is 0. Number 8. There we go. On what intervals are the function's values positive? Now, on number 1, I told you that we had the issue of having to be able to figure out what intervals something is positive, or what intervals something is increasing or decreasing on. This question is different. They want to know the intervals for which it's positive. So that means, where is it above the y-axis? In this case, it looks like it comes above the y-axis at -1. Stays above the y-axis until it hits 1, at which point it's 0. Remember, 0 is not positive or negative. And then it continues to be positive for the rest of the time. So that means we have -1 to 1 and 1 to infinity. Or in this case, they've just left it as x is greater than 1. Do notice that none of these are inclusive, because at this point it's 0, which is not positive, and at this point it's 0, which is also not positive. So this is the exact opposite question. It actually looks like, for me, this may be the same. Nope, it's not quite the same graph. On what intervals are the function's values negative? Well, it starts negative here, but that's not the first one they want us to worry about. The first one they want us to worry about is from 1 to 1. So at 1 it goes down to the negative, and it stays negative until 3. Again, 0 is neither positive nor negative, so these are open bracket, it's not equal to, it's just from 1 to 3. And then the other side, we see that all numbers less than -1, the y is negative. Traditionally, we would write these in the other order. This one would be written first and then this one, because usually you write everything from the left of the graph to the right of the graph. What are the zeros of the function? You will remember in one of the previous videos that you've seen that zeros of a function are where the y value is 0. So it's the x value when y equals 0. So this is our y-axis. Y equals 0 is right this line right here. So we're looking for 3 values. These are going to be the x-intercepts of the graph, and they are at -3. Notice that they want least to greatest, just like I told you on the last problem we normally do. So we have -3, 1, and 3. Again, your graph may look different than mine. We're already at question 11. Again, these last 5 questions are going to be the SAT style questions. So our model A equals 0.25t plus 29 represents the median age A of females in the United States as a function of time t in years since 1970. That's very important for us to remember. So 1991 is how many years after 1970? Well, 1991 minus 1970 is 21. So this is 21 years after. So if we're going to predict the median age of females in 1991, we're going to need to plug 21 into this equation. So 0.25 times 21, and then we're going to add 29. Well, in order to do that, let's just do it the easy way. So we have 0.25 times 21. 0.25 times 21 plus 29. I get 34.25. Going to toss in the parentheses to make sure that it did not mess with our order of operations. And yes, it did not, so we have 34.25. 34.25. Now, we do need to be careful here, because they want us to round it to the nearest tenth. I have it to the nearest hundredth, so I need to round this properly. 5 or above rounds up, so 2 plus 1 is 3. Predict the median age of females in 2020 to the nearest tenth. Well, 2020 is 50 years. 2020 minus 1970 is 50 years. So we can do the exact same thing, except here, instead of 21, we're going to plug in 50. And our median age becomes 41.5. So we'll plug in 50 here, 41.5. Checking our answer. Looking at number 12, part 1 of 2. Anthropologists who study skeletal remains can predict a woman's height just from the length of her humerus. This is actually true. This is something that's pretty cool. The bone between the elbow and the shoulder. So if you measure this part of your body, it's actually possible to estimate your height to some degree of accuracy. Obviously not. It's not going to be exact. So this table gives data for humerus length and overall height for various women. Using a graphing calculator, I'm going to use Desmos, find the linear regression model and its domain. That's something we've not taught you how to do yet, so you're definitely going to want to follow along. Enter the values of the slope and y-intercept to 2 decimal places. So we're going to have to take our Desmos And the first thing we need to do is add a table. And we are going to have our x and 1 and our y1. And what we're going to do is we're going to copy this table down. You'll notice that their table is horizontal. Our table is going to be vertical. So first value that they have is 35, and then 27, and then 30, and then 33, 25, 39, 27, and 31. Please, please, please note that your numbers might be different than mine. If they are different, plug in your numbers. 167, 146, 154, 165, 140, 180, 149, 155. I see I did make a mistake up here at 25. This should have been 140. 180, 149, 155. Everything else looks good. That was the easy part. However, if we zoom out, we're going to change our settings here so that we can get this. Looks like our smallest x is going to be 25, so let's go with 20 on the x-axis. Our biggest x value is going to be 39, so we'll go up to 45. On our y side, it looks like our smallest is 140, so let's go down to 120. And looks like our biggest is 180, so let's go up to 200. So here's our scatter plot. However, that doesn't tell us what the straight line that best fits that is. That's what they mean by giving us a linear regression model. So in order to get Desmos to do that, we're going to have to plug in something very specific. And you can watch me do that on the camera here. So we need y1. So if you just type in y1, it's going to give you that slide down. And instead of saying equals, we need to press this tilde key right here. But if you just press that, it's going to give you the bottom. So we're going to hold shift and press it, and that's going to give us the tilde that you see on your screen now. So y1, the way that reads is basically approximately equal to. Now we know that the equation for a line is mx plus b. So we're going to say mx, but we're using this x1 on our table. So x1 plus b. So y equals mx plus b. So as we're using that, we're going to have on our Desmos calculator, we can see that it pulled up the exact parameters for us. It gave us an exact slope and an exact y-intercept, which is what the MyHRW problem was asking for. They want us to, the linear regression model H is, H equals, well, the y-intercept is going to be, sorry, the slope is going to be 2.75, and they did want it rounded to 2 decimal places, so 2.75. And our y-intercept is 71.97. Double check that. 71.97. Yes. All right. Whew. Where L is the length of a woman's humerus in centimeters and H is her overall height in centimeters. The shortest length of a humerus given in the table is... the easy way to do this is just pull up Desmos and say, what is this? 25. The longest is, right here, 39. So the domain of the regression model is 25 to 39. Whew. Got it. All right. When L equals 36, H times 2.75 times 36 plus 71.97 equals, so the woman's height to the nearest centimeter would be blank. So once again, we're going to hop into Desmos, plug in 36. So I'm just scrolling over through the Desmos calculator to get to 36, and we can see that's 171.11. And I'm rounding it to 2 decimal places because that's what they had us do before. But then rounding it to the nearest centimeter would be 171. Because 36, we see that our domain is from 25 to 39. 36 is in that domain. So since it's in our domain of the regression model, the prediction is an interpolation. If it was outside of our domain, then it would be an extrapolation. Your prediction of the woman's height is incorrect. Enter the height to the nearest centimeter. I know what I did. So if we go to Desmos, so the mistake that I made was I was using the full parameter here. They don't want that. They want us to just use the numbers that they had. So 2.75 times 36 plus 71.97 is 170.97. So that was just a, believe it or not, the reason I got that wrong, the reason why this was incorrect, is because I was too accurate. So what I did was I went on the line that Desmos graphed for me and went to 36 and used that number. Unfortunately, that's not what they wanted. They had, because I used 2.75388, they wanted me to use just 2.75. So that's a mistake that's very easy to make. Hopefully you won't make it. Hummingbird wing beats rates are much higher than those of other birds. The table gives data about the mass and frequency of wing beats for various species of hummingbirds. So mass is here, frequency is here. Using a graphing calculator, find the linear regression model and enter its domain. Enter the slope and y-intercept of the regression model to 2 decimal places. Same question, different table. So we're going to go back to Desmos for this one. So I'm basically erasing all the problems out of the table. However, you'll notice that I'm not erasing what I had here for the regression model. And the reason for that is I can actually recycle that. So x1, we're going to have 3.1, 2.0, 3.2, 4.0, 3.7, 1.9, and 4.5. And for our y values, we'll have 60, 85, 50, 45, 55, 90, and 40. So, once again, we need to change our viewpoint. Smallest mass looks like it's 1.9, so we're going to go from 0 to Looks like it would make sense to go to about 5. And then on our y-axis, we're going to go from smallest is 40. Let's go from 0 to 100. All right. So now, once again, we can see our graph. We've got our data points, and we've already got our line here because we already had that plugged in. So what I'm actually going to do for the future is I'm going to log in here. Logging in with Google would allow you to save this graph. Instead of calling it untitled graph, you'd be able to save it so you wouldn't have to remember how to type that. So statistics, our parameters are negative 19.14. Oops. So we have negative 19.14 and 121.97. Where m is the hummingbird's mass and f is the frequency of wing beats. The smallest mass on the given table is 1.9. The greatest mass is 4.5. So the domain of the regression model is 1.9 is less than or equal to m is less than or equal to 4.5. Check. When m equals mass of 17 grams. Predict the frequency of wing beats for a giant hummingbird with a mass of 17 grams. So when mass equals 17, we're actually going to plug this into Desmos. We're going to have negative 19.14 times 17 plus 121.97. We get negative 203.41. Negative 203.41. Yeah. So plug in our 17 there. So the frequency of the wing beats to the nearest integer is negative 203. So this particular hummingbird beats their wings negative 203 times per second. Negative wing beats per second. Does that make sense? No, not at all. So complete the explanation on the reasonableness of the prediction and what, if anything, is wrong with the model. Is there anything wrong with the model? So, a negative wing beat frequency makes no physical sense. You can't beat your wings negative times. So the prediction is not reasonable. There is nothing wrong with the model. That's what I was going to say. There's nothing wrong with the model itself. The problem that we have is this prediction is an extrapolation, and it's based on a value of m that's so far outside the masses that we had collected that it just doesn't account for a hummingbird that's that big with such an extreme mass. All right, number 14. A student calculates a function's average rate of change on an interval and finds that it is 0. The student concludes that the function is constant on the interval. Complete the explanation of the student's error. The average rate of change on an interval uses only the endpoints of the interval in the calculation. If the points happen to have the same y-coordinate, the average rate of change will be 0. But that doesn't mean the function remains constant throughout the interval. We actually had a problem just like that earlier on this homework assignment, where we had two endpoints that were both at the same spot, but the graph was a U between them. So the function wasn't constant, it didn't stay the same, but the average rate of change was 0. Select the function in which the average rate of change on the interval -1 to 1 is 0, but the function is not constant over the interval. F of x equals 0, that's a constant function. We can see that if we plug it into Desmos. So I'm going to grab a whole new graph. So y equals 0. You see that red line tells us that it's straight up nothing. It's a constant. X cubed minus 4, well, that's cubic. But let's take a look at what that looks like. X cubed minus 4. That definitely doesn't look like it would ever have an average rate of change of 0, since it's always going up, it will always have a positive average rate of change. F of x equals x. Well, we're going to end up with the same problem here. It's always going up, so our average rate of change is always positive. However, the last one that they gave us is a simple quadratic. So on this one, we can see that from -1 to 1, the y value is the same on both sides. So our average rate of change is 0 because it's symmetrical about 0. I'm sorry, it's x squared minus 4. So let's go ahead and put the -4 so you can see that that doesn't change it. -1 to 1. It's still symmetrical about 0, so we're good. Final question. Complete the explanation of a way to obtain a linear model for a set of data without using a graphing calculator. After making a scatter plot of the data, draw a line that appears to pass as close to the data points as possible. Choose 2 points on the line to calculate its slope, and then substitute one of the points and the value of m into y equals mx plus b to find the value of b, the line's y-intercept. Enter the model as y equals mx plus b by substituting the values found for the variables m and b. I don't know why that's taking so long to grade. However, I can tell you that that is correct. So we have now done all of the homework assignment 1.2, and hopefully you will join me for the next video, homework 1.3, when it's time for you to do that.